Yeah. Okay. So recall that problem this moving car study is called the completion time of the multiple unicast. So we have a set of terminal pairs SITI and there are k of them. And now we want to ask what's the completion time of the network coding if each SI want to send to TI DI amount of information. I think in this work, we can assume, so for the, we show that for a network coding instance, like for graph of constant size, there is a network coding gap, right? And now we want to upper bound. So to upper bound the network coding gap, we need a lower bound on the we need a lower bound on the network coding completion time and an upper bound for the for the routing time. And this is how we relate these two quantities via the LP duality. And we want to show, okay, so from here it seems it's not obvious at all, like how you relate this to moving card that we defined last
yes,
time.
so
Yes.
question about the
Yeah.
primal. I thought the goal is to minimize T. And
Oh, right. So here what we want to claim, if Z is a constant, say is O1, then we have a routing scheme for completion time T.
right. Okay, so there's a specific reason to write.
Yeah, this simplifies the things later when we see the when we want to relate this to moving card.
Okay, sure.
Yeah, so this is the okay. So the framework will be assume the assume the routing completion time is T. Then for this, you will have a Z to be, say, constant.
Okay.
And then for duality for this, we want to say that, okay, if Z is a constant, then the moving card you have a lower bound on the moving card. So that's how we do. So there will still be some rounding procedure afterwards that we. So here, yeah. So high level, the dual of a multi-commodity flow is that there exists constraint for each pair of SITI. The distance, the weighted distance of SI to TI is lower bounded by something, right? Here is lower bounded by 1. But for a moving card, we still need some rounding. Like moving card, requires pairwise. It's not a SI to TI. Then we will do it. That's what we will derive next.
So here, the variables are the paths.
Yeah. So let's define them. Yeah.
Okay.
So for multi-commodity flow, PI, if there is no completion time constraint, this will be PI. That all the paths from SI to TI. Okay. And now you only look at paths that have length at most T. Okay. So this is defined as PIT. And the summation of these, like the flow on these paths should be at least Z times the defined DI. And all the other things, the constraints are the same as a multi-commodity flow. I missed something. Yeah. That's that's information right? So, yeah, this also for this P. Summation
But I guess is this this thing that you could go over all possible paths that goes through this edge.
Yeah.
Total information that you go through is T times. But is that what actually can happen? Because I thought in unit time you only send C.
Yeah. So so that's a very classic result. Saying if you have a flow of congestion, so this is a congestion, and you also have a dilation is the time of, say, the length of the longest path. you can always roll them in this part.
Oh,
Yes, the congestion plus dilation. Yeah, you use this to argue that there is a good routing scheme.
okay.
Yeah, so this says the congestion can be bounded, and then the dilation can also be bounded. So one way that if you yeah, so first thing, if it easy way to think about this is okay, if you are willing to lose another logging factor, you can just sample the time that you start to roll this packet. And they have like very small collision, something like that. But somehow you can you can also get rid of that.
Okay.
Yeah, good question. So that's about the primal that okay, so now I hope that convince you that if z is a constant, say at least 1/10, then you have a good routing scheme. Like okay, like formally there exists a rolling of completion time um yeah, so this is that one. Okay, and now yeah, let's take a look at this duality. So let's read what are these variables. So this is capacity of edges, right? And the variable in the dual is LE, that you assign a length variable to each edge. And this is saying like for each pair SI to TI, HI is a distance. Like the distance of T hop path. So you take all the paths of in PIT, and so the distance among these paths is lower bounded by HI. So again, this is only different with classic multi-commodity flow with this length constraint one. So yeah, so this is so for the normal multi-commodity flow, you need, so this you can replace by distance from SI to TI here under the metric L, right? And now why we need another variable is we only consider the path in PIT. So like PIT is defined, so in the original graph, all the paths of length at most T. And say for the original graph, let's assume they are the length is unweighted. Like all the lengths are unique of every edge. Otherwise, you just split the edges. And yeah. And yeah. So not any question about the dual?
Okay, so I'm still trying to understand what is each time. Okay, so here,
so yeah, let's say okay, like an intuitive definition can be this is a distance that under the metric L, and let's say it is T hop constraint of SI to TI. Yeah, this is a way to interpret it.
oh, okay,
right?
nice.
Yeah, you just you look among every path with at most T hop in the graph. Yeah, and the distance under the metric L should be a HI.
Okay.
Yeah. Yeah, let me just keep here. Oh yeah, so this is so this is let me see. Yeah, so now you already like renormalize it here, right? So consider yeah, do you see like why we have this constraint is by like combining these two when you derive the duality, right? It's like you're using the linear combination of that to upper bound the yeah, you want to upper bound z and I think this normalized, so that's why we have a 1 here. That is we normalize. Yeah, so this LE is like you take a linear combination of this inequality and that you need that many weighted constraints to the upper bound z. So yeah, so that's how we derive it. And to interpret this, I don't know a good way to interpret this. It's like a weighted distance is like this one. Yeah, it's just how we have this. I don't know like yeah, I don't know a good way to say like just from the inequality it says a weighted distance.
Okay.
Yeah. Yeah, so and just a high level idea how we relate this to moving cut. So here, at least you see the distance between the pairs, right? But we want something stronger to lower bound the network coding condition time. So there are several differences. So now this is the first one is this is a weighted, like the weighted combination, the linear combination of them is lower bounded by something. And I think for this we can use a bucketing, like to say, okay, if all the DI are the same, so we want we first lose a log of like D max over D min, like or like summation DI over D min, like the mean of DI, and we lose this to just like limit our scope into a subset of I such that their DI are similar. And then we can argue like for them, the pairwise distance is lower bounded.
Yeah, maybe okay, have a quick reminder, like what was the lower bound?
Yeah, so we need some moving cut. Yeah, moving cut. So we want, so it's a set of LE in C like integers. Like one, the total length increase is lower bounded, is upper bounded. DE LE minus 1 upper bounded less than, actually strictly less than summation. And 2, so yeah, for any pair edge, for the distance L SITJ is at least T2. So this, with these two assumptions, you have the any coding protocol. They call it mixed span our time. You can say coding mixed span is at least T. Yeah, so this is a moving cut. And now, yeah, seems to be much stronger than that, right? Yeah, we need to strengthen this. And first, they limit their scope to like one bucket, such that the DI among this bucket is like between a factor of 2, something like that, right? You can and lose this factor. You just like reduce the size of the indices by this.
Okay, so let's just run quick.
Yeah.
So the way is that we look at some solution to the rule.
Yep.
And then we try to somehow construct a moving cut. What was the
Yeah, the moving cut such that
please.
Yeah, like these things.
With
Like
the
for
method.
like you want to do it for a subset of indices in K.
Oh.
And then you say, okay, within this subset, you have a moving cut.
And the T here will need to be because the T there is basically the routing time for max commitment.
Yeah. So here it will be T. You will lose several factors.
Okay.
Yeah.
Okay.
Like including this one.
Okay. Okay, and then for this one, you're saying,
Yeah. So this is a trick. That okay. Let's first use bucketing. Let me first write down what we want to show. That we first want to show there exists a subset I. Such that and L tilde is this is E to C and you first want to satisfy this and guarantee some pairwise distance lower for C L E tilde minus 1 is at most Z times D summation of DI. Right. So if Z is a constant, then we are good. Right. So and then we also need to satisfy some weaker version of 2 is distance of L tilde SI TI. Like pairwise, it is at least T over some alpha gap. That the gap is this. Okay. And to show we can do this via bucketing. So I claim there exists a subset such that this subset I such that some mean that the mean hi is at least like 1 over alpha gap, and the summation yeah. So that okay. So actually we want to limit our scope so that like the distance the distance have a guaranteed like lower bound. Does that make sense? Actually, what I said like to
yes, so like the inequality directly says that if sum over all I h the di times the distance is at least 1, so you were saying you can look at one specific distance.
Yeah, but it's like how does bucketing work? Actually, I'm confused.
Oh, why didn't what you said? Like you bucket into
yeah,
according to the value of di.
You want mean of them. Oh yeah. I think that works, right? Because
the mean.
wait, it's not mean. Okay,
wait, it's the mean of it's the mean of the H line. But then does that mean you bucket according to H line?
Oh, right. You're probably bucketing across. Let me check it. Yeah, but why you have this?
Yeah, so I thought it's yeah, I don't know why it's this. Or it is this. Upper gap is
if you're bucketing through Asia,
yeah, it's very try about upper gap.
yeah. I thought this is simple, but it still takes some effort to
So if you bucket running through DI, then every group has roughly the same DI. They set it to be the same DI. Then oh, what's the mean?
But I think bucketing through HI should work, right?
Yeah, except why is that?
Yeah. Yeah, probably let's figure out this after.
Okay.
Yeah. So assume this bucketing result, and we have such a subset I. And let me just check if we have a lower bound on the side. I think we don't need to. Yeah, so we don't need to. Yeah, and now just assume this. We'll have like a metric L, like or say a length increase function L tilde, and that achieves a weaker version of Boolean. So
maybe for the first one.
Yeah, let me first write down what L is. Function L tilde is defined to be let's write it this way. Like around this integrals.
Oh.
And now this with -1, you will have this CE times LE times T times summation DI. And the summation DI will be here. So this and CE times LE times T is Z. Right? Yeah, so using this, yeah, you will first upper bound the summation of the length increase, and then to lower bound the distance. So this will be so at least h.
I guess the new distance is increased by t times the sum of the di.
Yeah. Right. So using that thing, and it is increased by this, and di summation di, like rearranging term is lower bounded by 1 over of a gap. But what about the h? I think I missed. Because you have summation di is at least 1 over mean hi times so and this let me overbound this. So this distance is at least in z is at least hi times d summation di and summation di you rearrange the term is and summation di times mean hi is at least 1 over alpha gap. So this thing will be at least this. Okay. Okay, now let's compare them, right? So the first thing is good because it is constant, and the second one is pairwise, right? And this is all pair.
Yeah.
And fortunately, there is a lemma is from so from pairwise to all pair distance. So given any metrics. So in K pairs. So for any I that the distance any metric L outside here is like this. Then I claim there exists a subset, a prime subset of I that and prime is at least okay. Let me use D I over 9, and this guarantees pairwise. So distance and I Tj at least T over log K. Like for any pair.
What do you think?
The size of I. So yeah, so this is previous result that it works for a lot of metric space. Like for L2, you even have a square root. This you only pay square root. Yeah, but this is for general metric.
I see.
Yeah. And then we can go from here to here. But now when you give this talk, what I actually make me curious is why we actually care about the size. Like if a subset that is that also if we go from here to there, do we also lose this constant somewhere? Probably, right? Like we probably lose 9 here, right? Okay.
But that's important. Oh.
Yeah. So that's why I care about this. Like like if what if we lose a super constant? Probably that's not good.
Yeah.
Okay, yeah. So but fortunately this you can see this we only lose another log factor in here.
Okay, yeah.
Which we can tolerate. Okay. Yeah, like overall it's still polylog. So assume this thing is it's a log then it's something like log squared. Yeah, if all the domains are unit, then this is log k. And this is log k. Yeah, then we combining this with this, we have already upper bounded the network coding gap to be say polylog k. Polylog k. Right, this is informal, like actually log k times this. Yeah. And the lower bound is to use graph product to boost the instance we talked about last in the last talk, and this is what we will talk next about Mark's paper. So they use the same technique, yeah. But theirs is more complicated because it's still like you have two things. One is the completion time, and the other you still have some. Yeah, this you can see this is like a more generalized or say more complicated version of multi-commodity flow. So yeah, it takes more steps. So that's why I want to present Mark's graph product.
Are we right?
So yeah, so this constant depends on the original graph G. So G.
One plus x.
Yeah. Yeah, let's say this graph is yeah. So if we have a small graph, usually constant size, right? Like the example we showed last time, it's it achieves a gap of constant larger than one of completion time, and then like there are some analog of this theorem for that setting, also boost that to logarithmic. Yeah, and this one is in throughput setting, the one we will talk about today. Yeah, so let's talk about the high level idea. So what if we have a graph, let's say G, and then we want to say, let's draw some simple graph. Okay, this doesn't illustrate the gap, but let's use it for an example. What if I replace each edge by some other instance of network coding, like you are recursively creating network coding instance, because here an indirect edge is sending some information, right? And you want to say, okay, now like within this, you want to create some network coding instance, such that it's more efficient to like inside this instance using some network code. The hope is that, okay, this is G1, and like you use some G2. I have not tell you how to replace, but then you want to achieve something some network calling gap of this thing times this 1 plus epsilon 1 times 1 plus epsilon 1. And the way of doing this will be, okay, let me draw some simple examples. Like, what if I replace inside with another so cool. Yeah, so let's label them. This is S11, as the T12, T11, S21, T21. Yeah, so like the second label is saying which copy of G2. Let's say each here this is some G2. So this is G1, and inside there's a copies of G2. And say we, yeah, like, but we want to use each instance for now, like we cannot create this because this S1, S21 and T21, they are not used for communication, right? And then so the kind of idea is that okay, we need multiple copy of G1. And then say for another copy of G1, you can create this way.
Sorry, again, why is this not? So
okay, if you just embed the graph like this, so this is, so what you actually want to simulate is for each G2, you want G2 actually perform another network calling instance.
Yeah.
But now S21 doesn't need to communicate to T21. So because now these are fake terminals.
Well, actually, when you create a larger graph, the number of pairs does not increase. Can you increase the number of pairs?
Yeah, good question. So if you take them as terminals,
yeah,
I will assume it's not a product anymore because like just using this, ignore this, you will fulfill the requirements inside here. So you really want a product, then you need this terminal pairs also act like an edge, like of some instance G1. Like it's like you really want them to be like one is outer, the other is inner, and the product. So that's why we need another copy of G1, and let me draw. So this thing is connect to another copy of G1. This is S1 prime, and say, and this act as a like the first edge again, right? Then this is S2 prime. Right, so here this serves as this edge for the second copy of G1, and again, like you can just connect them in a good order to complete this graph. So right.
I see.
Yeah, and this actually shows how we design the graph product. Is that we actually want each copy of G2 to serve different copies of G1. Like in this way, the hope is really, if you really want to do something not following the rule, then you need to hop between different G1, which is not. That will actually take more effort. So that's high level, and I will like formalize this idea. Yeah. So formally, you want a bipartite graph. So each vertex on the left is a copy of G1. So I want to formalize this structure. So this is like N1 copies of G1. And n2 like n2 copies of G2. And there are edges here that with label. So this is that you need a pair. Okay. What is the label? I want to call it. Let's probably just call it AB. Yeah, so the first index indicates okay which edge that you want to replace in this copy of G1. And the second index will be like for for which communication pair you want to use for this edge. Right? And now it's like for each edge there is a color on it with two labels. And what you want is okay for each edge you want someone to like to replace it, and here like for each products here you want to use every color. So it's like if you do a restriction, it should be a rainbow, like the color of the edges should be rainbow if you only look at the first index of the neighbor of this guy, and it will be rainbow if you only look at the second label, like around each vertex on the around the right hand side. Right. And then one more constraint is that if you look at one vertex here and all its neighbor edges, the first index will be the same. It's saying all the communication pairs in this graph are used to replace, let's say, the same edges in different copies. Okay. So what we need in this is that, okay, even you hop from some instance to like, okay, in the final, like in the product graph, even if you are cheating, like you hop to some other places and they are their shortcuts. So in this way, so you want to say no, because you still stay on this edge. Like if even like you want to go to your final destination and you hop to other places, it doesn't help. So that's a header value. Yeah. Yeah, but formally you still need LP duality and the proper assigning the variables. Yeah, and now we really need colored this kind of colored bipartite graph with high girth. So with high girth means so yeah, so with high girth means there's no shortcut. But let me formalize this a little bit more. Yeah, yeah, let me think. It's a so I want to
So what happens if there's a dot cycle?
Yeah, so yeah, now I wonder, yeah, because if you see the proof is saying with high Gerson there is no shortcut, but let me think about the why high level.
Yeah.
Why the argument I already give you not suffice, right?
Yeah, right.
So Oh, I see. So it's probably related to another problem here. So what if there are multiple terminals on the same vertex in this say in G2? Then it seems not obvious that like you probably can cheat again, right? So this the wait, let me think a little bit more. Yeah, probably I need to think it again. Yeah. Yeah, but just let me just talk about something I understand.
Yeah.
Yeah, for this I confused. So yeah, so still the high level idea of proving this is you go to the dual solution again. And you want to you want to upper bound the wait, you want to upper bound the routing, right? Then you need to assign like the variables of dual of the product graph. So that you give a dual solution. Then you give a like an upper bound on the
sorry, which way I'm going? So assume that the smaller graph has a gap. Then assume that you have a that now you directly bounding the gap for the product graph, or we're trying to say that we can use the protocol for the product graph to derive the protocol.
Yeah, so okay. So for the product graph, one thing is easier. So there still exists a network coding solution. You just like it's natural, right? Like how you send this information is like you just use the network coding solution of the G2 etc. Yeah. And then I think the harder part is to upper bound the routing throughput. So you have a lower bound of the network coding, and then you have an upper bound on the routing that creates a gap.
With it.
So you want to here you want to lower bound the gap. So yeah, it's different from what we did there, right?
Yeah.
That for that we want to upper bound the coding gap. Yeah. So here yeah, so because for network coding conjecture, the upper bound is still trivial. People doesn't know anything, and otherwise you will have some strong implication of that. So here we only consider lower bound. So to upper bound the routing throughput, the idea is to assign variables to the dual of the LP, right? That will gives you an upper bound. Yeah. And the way is actually simple is that for each edge, like for each edge here now you just assign the product of the weight of the original G1 with the weight of this edge. So it's like you again doing a product.
Okay.
Does that make sense? And because you like summing over any path, it's like you're producing L1 with L2. Yeah. Yeah, if you have time, if you have the other, yeah, other, yeah.
Thank you so much for doing this.
Yeah, thanks for attending. Yeah. Yeah. Yeah, then this will be a lower bound on the length and I think this high girth is for preventing you from shortcuts. But now I need to figure out. I need to.
Yeah, so don't see where I can take.
So what if like multiple terminal pairs lies on the same vertex? Will that create some shortcut?
But where does the proof break? I thought
Yeah.
you already signed weights to all the edges and then somehow show the.
Yeah, I need to figure this out.
Okay.
Yeah. Yeah, I think it's like 15 minutes. Let me first end this recording.